Hey Scholarship kids, and welcome to Lesson 7 Part A. This is our last lesson on redox, and so the exam questions we're doing today are 2016 and 17. Cool, let's get started. So this is from 2016. A very dilute solution of sodium cyanide can be used to extract gold from its ore. Very similar question to what we finished on in Lesson 6. Gold reacts with oxygen gas in the presence of cyanide ions to form this complex ion. It's carried out in basic conditions to ensure that cyanide ions are not converted to toxic hydrogen cyanide gas. So that's why it's done in basic conditions, which if you remember, we actually discussed that in the last question of last lesson to do with the equilibrium of HCN being a weak acid. Okay. So gold is then recovered, which means, so if these are gold ions here, so if it's recovered, it's being turned back into a metal by reacting the solution with zinc. So that means that zinc gets oxidized and the gold gets reduced back into gold element and metal, and the zinc gets converted to this complex ion. Sometimes the recovered gold also contains elemental silver as a small impurity, and this silver impurity can be recovered from the gold by reacting the mixture with nitric acid. It says discuss the chemistry occurring, identifying oxidation reduction processes, use electrode potentials, which means you need to have balanced equations, and explain why gold can be extracted in this way, and it says, and talk about separating gold and silver with nitric acid, so why we can separate the silver from the gold and the gold won't react. Cool. So the next thing to note is that you were given all of these reduction potentials, and actually some of these reduction potentials relate to a question in a little bit from the 2016 exam. I've actually copied these into the next slide that I'm talking about. They'll be a little bit small, but you'll get the main gist here. So I've kind of just popped this sentence down here. Gold reacts with oxygen gas in the presence of cyanide ions to form the complex. So here are the two equations. Well, what I did is I first of all went, okay, well, where's the oxygen equation? Because it's saying that it's reacting with oxygen. And when you look for the oxygen equation, there are two. So there's this one here and there's this one here. And it said it's basic conditions. And that's really important because that means it has to be this oxygen equation and not this acidic one. So that was quite important. So I've just copied that reaction down. And then the next thing is that I'm looking for a reaction where we get the cyanide ion, the gold cyanide ion, apologies. And so I've just gone, well, where down my list does this appear? And you see it here, okay? And so I've put those both down. Now, what you'll notice here is that this top equation needs to be flipped. And the reason why is because we have to start with elemental gold because that's how gold exists in its ore. It's just that it's stuck with other impurities. And so that means we have to make sure that this top reaction actually gets oxidized instead and the bottom reaction gets reduced. And when we do this, and just to confirm, it's because we know that Au exists as the element in its ore. So we flip that around and you'll see that I had to times this first equation by 4 to get 4 electrons. And you can see I've written it out here because you always have to do a fully balanced equation. And then I've calculated the cell potential by doing reduction minus the oxidation. And we get a positive cell potential, which means this reaction is spontaneous and will occur. Okay, so we can use cyanide ions to react with elemental gold in the presence of oxygen, and it'll form this complex ion. Okay, now it asked us to link to redox, so what was getting oxidized, what was getting reduced. So Au was the reductant, okay, starts with an oxidation number of 0 and it's oxidized to +1 in this complex ion. So just if you're not so familiar with complex ions, we haven't got to 3.6 yet where we do a whole bunch again on complex ions. How it works is that the charge on your complex has to be equal to the charges inside. The cyanide ion, as you can see up here, is 1-, so there are 2 of them, so that makes -2. And so if this complex has to equal -1 because of this charge here, what plus -2 equals -1? And the answer is +1. So Au must have an oxidation number of +1 in the complex ion. The oxidant, therefore, must be oxygen, and we know that because it's getting reduced, and it has an oxidation number of 0 as O2, and it's reduced to OH minus, which has an oxidation number of -2. You could go on and say that, a decrease in ON equals reduction and an increase in ON equals oxidation. And actually probably should. That would just complete the answer. But all in all, that's the first part of the answer as to explaining the process of that part that they've explained. So let's keep going. So the next part is them getting the pure gold back. And how do they get the pure gold back? They react with zinc. So what I did is I know that this has to be the gold equation because this is the only one that had the gold complex. And this is what we've got right now from our first reaction. And then if you go down your list of cell potentials, they'll only give you one, so you can't kind of get too confused. And in fact, I can't even, trying to find it, oh yeah, down the bottom. And here's the zinc one, and that's the only one with zinc in it, so you ain't got much choice. It has to be that one. And so when you put the two together, we know that this is what we're starting with, and so we know we have to reverse the top one and make it oxidation. And we know that anyway because it said you were adding zinc, and it said that zinc was reducing the AU. So we know that's getting reversed, and when you reverse it and write a full equation, this is what you get to. And I hope that makes sense. So this should be superscript, by the way, and with my broken keyboard at the moment, I can't do that. So I'll go back at some point and fix those on your notes, but I'm sure you guys can cope with that. So your zinc's getting oxidized here, okay, and your AU's getting reduced so that you end up getting your pure gold, which can be recovered. When you do your cell potential, reduction minus oxidation, and you get a positive value, which means the reaction is spontaneous. So this will occur, and this is how they do it, which is pretty cool. So it then says when there is a mixture of AU and AG reacts with nitric acid, as it can be oxidized by nitrate ions, which oxidizes Ag to Ag aqueous. And so what we have to do here is how can we separate the Ag from the Au? Well, the Ag must be a spontaneous reaction and the Au must not, or else you wouldn't be able to separate them because they would both react. So I've from that big list of cell potentials, I've just noted down the ones where you have pure elemental gold and silver because that's what they said reacted, and then I've pulled down the nitrate one, and again these are all reduction. So if you're starting with these two, that means that these two need to be reversed so they can be getting oxidized, and this one's getting reduced because it says that in the question. So therefore, if we do a full equation, which you can see here, there's 3 electrons in this one, and then if we react it with Ag, first of all, we need to times this one by 3, and we'll have to do that for the gold as well. There's the full equation, remembering you've got to do a full equation to get full marks. And then I do a cell potential, reduction minus oxidation. I see it's positive, which means that we can use nitric acid to react with gold, and a reaction will occur, which is really cool. Okay, and that means that we can extract the silver. And then the only way that can actually work is if we can't extract the gold in the same way. So we do the same reaction, but we do it with the second one here with the gold. And you'll see that when we do the cell potential, reduction minus oxidation, it's negative, so it won't occur. And that's how come we're able to separate the silver impurity and leave our pure gold, which is pretty awesome. So yeah, so that's explaining the question. So here's the next question that we're going to go through today. This is 2016 2B. So iron ore, Fe2O3, in a rock sample can be analysed by titration with acidified potassium dichromate. So the first thing to note is they're telling you that the titration that we're focusing on today is between Fe in the iron here, in the iron oxide, and this and dichromate, okay? So this is the main thing. It says 2.831 grams of hematite rock containing Fe2O3 was dissolved in concentrated hydrochloric acid. That's purely just to dissolve it into the aqueous ions. And the solution is diluted to 250 ml in a volumetric flask. 20 ml samples were pipetted, and it says that tin chloride was added. Okay, so tin chloride was added and it changes color, telling you that something's reacted. So that's why they're telling you that there's been a color change. So you know that a reaction has occurred here. And a saturated solution of mercury 2 chloride was then added and a small amount of white precipitate appeared. A few drops of this indicator were added and it was titrated with potassium dichromate. The average titer value was 18.56 and the standard solution of potassium dichromate was made by putting this mass into 500 mils because dichromate is a primary standard. Now, it then says calculate the percent composition of Fe2O3 and explain why it's not appropriate to carry out this titration using potassium permanganate. Let me first of all say they try to confuse the hell out of you with all the writing in this question, all these reactions that you're not going to know about. And so that's what scholarship is going to do, and you have to wheedle out the information that's actually important to get to your answer. And often you guys can actually get marks straight away, like most of you should be able to understand by now how to calculate the concentration of a primary standard. So if you just worked out the concentration of that, you'd get something, and then you can go from there. So I'll talk you through it. As I've said here, most of it you can discard, but in Fe2O3, if you guys balance that out, you know it's an ionic compound, it's Fe3 plus is what's in there. Now we know the titration is actually between, is with iron and dichromate, right? But we know dichromate only ever gets reduced, which means our iron must be getting oxidized, which means something is happening to the iron, and we must actually be reacting the dichromate with not Fe3 plus, but Fe2 plus, because it has to be able to be getting oxidized, and we can't oxidize Fe3 plus any further. So therefore, there has to have been some reaction in that massive paragraph where Fe3 plus reacted with something to form Fe2 plus, so that the Fe2 plus is what actually is reacting with our dichromate. And if you look at the question, it says really clearly here that the acid is used to dissolve. So the hydrochloric acid is to dissolve it and form aqueous ions. So it's not likely to be that. But then it says that excess tin 2 chloride is added. So excess is always added to make sure something completely reacts. So there's a bit of a hint there when it said the excess. And it said that there was a color change. So a color change tells us that a reaction happened. And so what's actually happened here is the Fe3 plus has been reduced to Fe2 plus, and the tin is getting oxidized. So that's what's happened, and you don't need to worry about the equation. All you need to know is that all of the Fe3 plus that was in our sample got converted to Fe2 plus, okay, by tin, and we know all of it reacted because the tin was in excess. So now we've got Fe2 plus, and then blah-de-blah-de-blah. This stuff is just trying to be confusing, and we titrate with dichromate. And so it's the Fe2 plus and the dichromate Cr2O7 2- that are reacting. So I hope that makes sense. Again, you might have to read the question a few times, and they're just trying to trip you up by everything, and I'm not going to go through every part of it because it's irrelevant. We just need to keep focused on the stuff that's really key here. Okay, so the next thing is that I would always start by calculating the concentration of that primary standard because it's nice and easy. They gave you a mass of the dichromate, and they gave you a molar mass, and so we can do mass divided by molar mass to get a mole. They gave you the volume as being half a litre, so therefore we can do, and that's, just cross out that gram, sorry, and do number of moles divided by volume, and we'll get moles per litre. So there's our concentration of our primary standards. That's the exact concentration of dichromate used. And then just to make sure we're clear, this is actually the titration we're worried about. Dichromate gets reduced to Cr3+, and Fe2+ gets oxidized to Fe3+. Now, I've not bothered doing the half equations, but please make sure that you can actually get to that full equation. By now, you should be able to. That's no harder than level 2. So what I'm going to do here, folks, is I'm going to pause at this point and I'm going to start video B, and it will be quite a short video, and then I'll show you the homework question. Okay, team, see you soon.